Okay, so we are happy to have with us today Eirini Chavli from the University of Stuttgart, who is going to talk to us about Nakayama algebras via combinatorics.
Okay, so firstly, I would like to thank you very much for the opportunity to give a talk. I think I have talked about this topic in 2022. We had a conference in Athens, but in 2024, we revisited this project with my uh, co-author, René Marczinzik, and we realized we can do some other things also. And then we have changed the proofs. Anyway, so I'm going to present one more this topic and give you the new proofs and the new results we have. Okay, so before I start, I want to tell you that this project, what I find interesting in this project is that on one hand you have representation theory and homological algebra, okay, and the object is the Nakayama algebras, and then you do a translation, and you can use combinatorics to solve problems. And I found this very interesting somehow that we can find answers from combinatorics to representation theory. Okay, so I'm going to introduce first the Nakayama algebras, and I will talk to you about the problems we had with René. Then we will talk about the combinatorial objects we are going to use, and at the end I will give you the results. Okay, I will start with the Nakayama algebras and the motivation. So when I will start with a classical problem of representation theory. Let A be an algebra defined over a ring, which is commutative and Artinian, and we assume that our algebra is finitely generated as R module. A very, very classical question is to classify the indecomposable finitely generated A modules. So this question is open for many classes of algebras, and we have only a few ones for which we know this classification. And among them, we have the Nakayama algebras. So we encounter the Nakayama algebras in representation theory of finite groups. So if G is a group and F is a field, and if we assume that the group algebra Fg is of finite representation type, this means that the number of irreducible finitely generated modules are finite. Then if you take the category of Fg modules modulo the projectives, then this is isomorphic to the A modules modulo the projectives, where A is a Nakayama algebra. So for the people who are not so much into representation theory, and now I say modules and things like that, don't worry, because we won't use them in this talk. So I just give the motivation for the Nakayama algebras. So secondly here, if the characteristic of our field is not zero, and if we assume that our group admits a P-silo subgroup, which is normal and cyclic, then we know that the group algebra is a Nakayama algebra. So as I told you in the beginning, these algebras appear naturally in the representation theory of groups. And we have a lot of applications of Nakayama algebras. So we can use them to classify Brouwer tree algebras. We use them in algebraic geometry. I know nothing about these two topics, so I hope you don't ask. And then we use them in order to study combinatorics of Dyck paths. I told you in the beginning that we do the other way in this talk. So we use combinatorics in order to study these algebras. Usually it's the other way around. Okay, so let's define now these algebras. And I will start with the definition of a quiver. So what is a finite quiver Q? As you see here in the example, we have an oriented graph. And I say finite because we have a finite number of vertices and a finite number of arrows. So what we see here in this example is that, okay, we have our vertices, and then I allow multiple arrows, like here I have F1, F2, I have 2 arrows, and I also allow loops, like you can see here with the G. And every time we have an arrow, it starts from a vertex that we call it source, I like to call it head, to some vertex, which we call it tail. Okay, now when we have a finite quiver Q, we can define paths. So what is a path? We take arrows that we can concatenate. And okay, if we have 2, 3, n arrows, then we have a path of length n. And also, if we have a vertex, this is also a path, but this path doesn't have a length. It's a path of length 0. I mean, it has a length, it's the 0 length. And we say here that the head of a path is the head of the first arrow in the concatenation, and the tail of our path is the tail of the last arrow in the concatenation. So I give you here an example. First of all, I hope you can see my mouse. Can you see my mouse? Someone can. Anyway.
Yes, we can.
Yes, okay,
Yes.
because I'm going to use my mouse a lot later. Okay, so we have V1 here, this vertex is a path of length 0. Then I have just an arrow, H, for example. This is a path of length 1. And then I give you here an example, G2, then I go to H, I do my loop, I go F1 and I, and this is a path of length 5. Okay, so this is the quiver, we have the paths, and now we are going to define an algebra. And in order to define an algebra, we need to multiply things. So how we multiply two paths? If I have two paths, and I can concatenate them, which means that the tail of P is the head of Q, then P times Q is the concatenation. If this is not the case, then we say that P times Q is 0. So 0 is a new element, we construct it like that, and we call it the 0 path. So, okay, in the example we saw before, if I take as P to be the path EG1, a path of length 2, and Q is G2, if I do P times Q, of course, I concatenate, it's EG1, G2. But if I do Q times P, I cannot concatenate, so like that I have the 0 element. Okay. So now we have a multiplication, and we can define an algebra. We fix a field, K, and the path algebra KQ is the K vector space, okay? And the bases are all the paths in Q. And if you wonder about the identity element of this algebra, I mean, okay, let's see here with the example of I. If you multiply I with V2, you have I again, because V2 doesn't go anywhere. But you cannot multiply I with V4, for example. So in order to have the identity element, you take the sum of all vertices. So every time you multiply with the path, there is a vertex that it's the tail and it gives you the path, and the others are the 0. Okay, so what's the problem so far? I mean, okay, we define this algebra. Okay, it's a K vector space. We know the basis. The problem, if we want to say it like that, is that this basis has infinite number of elements. And you can see this in this example, because if you have G here, which is a loop, you can multiply it with G, G. You can have an infinite number of powers of G as paths. So the basis is infinite. And in representation theory, we prefer if we have finitely dimensional algebras. And that's what we're going to do now and have the Nakayama algebras. Okay, so for the Nakayama algebras, we need a particular quiver, which is either the cyclic or the linear. And we have two possibilities. I was going to say Möglichkeiten, okay. We have only two possibilities, because I don't know if you remember the first slide that I told you that the Nakayama algebras appear naturally in the representation theory. And I gave you two ways to see that. So one corresponds to the cyclic quiver and the other to the linear quiver. Anyway, So we have either the cyclic quiver or the linear quiver with n vertices, okay? And we construct the path algebra. And now we want to have a finite dimensional algebra. So what we do? We take J to be the ideal of generated by all arrows. This is the Jacobson radical of the algebra. Okay. And now I stabilize an M, which is bigger or equal than 2, and I choose an ideal between J to the M and J square. And if I take my path algebra modulo this ideal, then we have a new algebra, which is called a Nakayama algebra. So what I do in practice, for example, think about the cyclic quiver. If I have the cyclic quiver, I can continue doing circles all the time, which means that my dimension is infinite. But now, with this choice of this ideal E here, I do the following. I stabilize my M, and I say, okay, all the paths that they have length more than M are 0. So like that, the dimension becomes finite. So something that it's not clear the way I have written that is that every time you stabilize your M, you have sometimes more than one possibilities to choose this ideal I. That's why here in the definition and the name I have given to the Nakayama algebra, I give you the N, which is the number of vertices of the quiver, and also the ideal. Okay, let's see an example. So let's take the linear quiver that has 4 vertices. And let us choose now this ideal I. Okay, the first thing one can notice is that we don't have so many choices of this M. Why is that? Because in this quiver Q, I cannot have paths of length more than 3. All the paths that are of length 4, 5, 6 are 0, because, I mean, how can you concatenate 4 arrows here? Which means that M can be 2 or M can be 3. Because if M is 4, then this gives you nothing, and you only have to consider this relation that you consider anyways. Which means that in this quiver, whenever you choose the Nakayama algebra, in order to find the ideal E, you have the ideal E is an ideal generated by linear combinations of paths of length 2 or 3. At least 2, sorry, yeah. Okay, let's do that in the example. So here I have the 0 ideal. Here I have a path of length 2. It's alpha 1, alpha 2. I take also alpha 2, alpha 3. Then I take both of them, alpha 1, alpha 2, and alpha 2, alpha 3. And then I take a path of length 3. So I've seen, when I was working on this example, I have seen some other possibilities also. But if you have something else here, then it's isomorphic to these 5 cases. Okay, so the question now is, okay, why do we have 5? What is this 5?
Sorry, Irini.
Yes,
For the last example, you have a path of length 3. Could you
yes.
maybe explain more the condition on the ideal I? Because it seemed to me that it means you only have to choose for paths of length 2,
At least 2.
at least.
Because you take at least 2, because, okay, if this is M here is 2, so
Mhm.
here you have at least 2, because this I is inside J square. But if M is 3, then you have only this one.
I see. And for the linear quiver, this algebra will generally be finitely generated.
Yes, and for the
Okay.
cyclic, this Nakayama algebra. And there is a formula for the dimension, which is very complicated. I don't remember by heart, but yeah, this algebra is of finite dimension. Are there
Thank you.
any other questions?
Yes, sorry, Irini, I have also a question. If Kostas has
Yes,
finished.
yes.
But if it's the cyclic one, then you can go on, like you can have paths of any length, no?
No, because you have here modulo this ideal.
Ah,
That's the idea. I mean, when I take my Nakayama algebra modulo my ideal, what is this ideal? This ideal tells you that when you have paths of more than m, these paths are zero, so you cannot continue infinitely the circle. It stops when it stops m, when you do the circle m times.
Okay.
Yes, no?
Okay.
So, are there any more questions? Okay. So we have here 5 choices, and let's explain these 5. So this 5 is the Catalan number C3. And I tell you like that, the 3, because remember we have 4 vertices. So we find here the Catalan number C3. And this is actually a general fact. Whenever you have the linear quiver, if you play this game with the ideals, then you end up with Cn-1 Nakayama algebras. So what does it mean? It means that you can associate the set of Nakayama algebras with some sets of combinatorics enumerated by the Catalan number. Okay, and this is very nice because then you can translate Nakayama algebras through combinatorics. Okay, let's see now another way to see these Nakayama algebras that I'm going to use later to describe these bijections I talked about between Nakayama algebras and combinatorics. So for the representation theorists fun, when you have a Nakayama algebra, you can have some idempotents which are indexed by vertices. And then you can define here a series of n positive integers, and each integer here denotes the dimension of, typo here, of the decomposable projective module here. Okay, but if you're not familiar with indecomposable and projectives and whatever, so in order to find this Kubi series, you check your quiver. I mean, actually, you check your path algebra modulo, this ideal, and you check all the paths that they start from the vector, from the vertex I plus 1. Okay, let's see here in this example. Okay, I will explain one of them, maybe the second one. So I have this quiver, modulo, alpha 1, alpha 2. Okay, let's find all the paths that they start from 1. We have the vertex 1, then we have alpha 1, and that's it, because alpha 1, alpha 2 is 0. We take modulo this one. So we have only 2 paths that they start from the vertex 1. Let's go now to 2. We have the vertex 2, then we have alpha 2, then we have alpha 2, alpha 3. We have 3. From here, we have only 3 and alpha 3, and at the end, we have only 1. So what does it tell us? First of all, when you have the linear quiver, maybe you see that if you take this Kubi series, at the end, you always have 1. Because if you have the linear quiver, the only path that has as a head the vertex n is n. Which means, if you go here to dimension of modules, that this module here that comes from the idempotent is of dimension 1, which means it's simple. Okay. So the interesting thing here is that this is a theorem of Frank and Fuller, is that if you know the Kubi series, you can find the Nakayama algebra, and vice versa. If you have the Nakayama algebra, as we have seen here, you can associate the Kubi series. So from now on, when we talk about Nakayama algebras and we need to build something, we will build the Kubi series. Okay. And from now on, we will work with the linear quiver. Okay, let's start now with the combinatorics. So the first object from combinatorics are the so-called Dyck paths. So what this is a path that starts from the point 0, 0, and it goes to point 2n, 0. The number of the up steps is the number of the down steps, and it's n. Every time I go up, I add the point 1, 1. Every time I go down, I add the point 1 minus 1. And I have only one rule. I never go below the y equals 0. I never go below this axis here. And there is another way to write Dyck paths if you don't want to draw them. So you write them with the ups and downs. I mean, in this example, I have 3 times up, 2 times down, 2 times up, 3 times down, and so on. So we know that the number of n Dyck paths is the Catalan number Cn. So what I tell you here as a theorem is that if you have the Dyck n paths, and if you have the n plus 1 Nakayama algebras, remember we had the example n equals 4 and we found C3, then you have a bijection. And now you will tell me, okay, Eirini, this is not very sophisticated to present to us as a theorem, because you have 2 sets with the same cardinality. So, okay, of course there's a bijection. But the reason I say here theorem, and actually I'm not sure if it was Ringel, but it's the only reference, the oldest reference we found, is because actually he built this bijection. And this is very important because when you want to pass to combinatorics and you have, for example, a Nakayama algebra, you need to know exactly what to associate. So I'm going to describe you now how this bijection is built. With an example, of course. We take here the linear quiver and we take this Nakayama algebra we saw before with a cubic series 2, 3, 2, 1. I put some colors here in order to draw. We take here, maybe, I hope you can see, this is a bold line. This is the y-axis. So what I do, I pick a diagonal and I start from the right and I go to the left and I put here the points that cubic series tell me. So now you see what is the Dyck path, and you can do it the other way around. If you have the Dyck path, of course, you can find the points in the diagonal, and then you can have the cubic series, and as I told you before, then you can have the Nakayama algebra. Okay, so now
But the part where you pass from cubic series to the Nakayama algebra, is there an easy way to see the structure of the algebra from the cubic series, or just?
No, that's why it's a theorem, and it's not very easy to see how you pass. Of course, you can describe the quiver, but the structure and everything, no, it's not very easy to see.
See.
Eirini, what about the green dot that you leave out? You
will see now.
Like you have to go up all the way and then down. How?
You will see now what is the Greek dot that I left behind. But actually, I mean, if you put the dots, then it's only one way to find the Dyck path. And there is a meaning of the one I left out. I will explain to you now. But if it's like that, I hope you all can see what the graph is.
Couldn't it go down after the second red?
You mean black, green, green. And then what do you do with this red one?
Well, you left the green out. Why not leave the red out? I don't know.
Because, okay, I know what you mean. I don't want to leave, I mean, things from behind, I don't mind leaving them out. I don't want to leave things above. So I want, when I do my graph, that all dots are included down of the graph.
Okay.
Any more questions? Okay. So thank you for the green dot, because this is what I was going to tell you now. Okay, so we have an algebra, which means that this algebra, we can do some representation theory with this algebra and talk about modules. And one step further, indecomposable modules, which are the building blocks of every module. So I'm going to, what we did with René is, and it was what we did in 2024 actually, is to translate all this in the Dyck path. And because I need some vocabulary, I am going to spend a little more time, just one slide, to say something more about modules, and then we are going to see everything using our Dyck path. Okay, so I take my Nakayama algebra, and I take an indecomposable module. And I say here then, I cheat a little bit because this is a theorem, then this module is finitely generated. So I take a system of S generators, for example. And then I can define here this map. So I take here coefficients, they belong in my algebra, and I build linear combinations. Okay, you can see that this is a surjection because every time I have an element in M, I can write it as a linear combination. So I just consider the coefficients. Now, if my module is free, it means we have a basis, this linear combination is unique. But this is not always the case. So in order to study how far I am from having something free, I'm going to study the kernel of this phi, which is what we call first, oh my God, now, CGG. I cannot say this very well. It's the first CGG of M. And it turns out actually that this first CGG is isomorphic with an indecomposable module of the algebra. Okay. Let's now see this in the composable module. So I have here a picture. For the moment, ignore the colors and just see these black dots, which were the dots Maria said before I left out. So all the black dots, which come from the Kubi series, if you remember, are all the indecomposable modules. So instead of having in my mind indecomposable modules, I just have these black dots. So let's study one of them. Let's study, for example, this red one. Okay? So if you see, this red one belongs into two diagonals. This diagonal, that I call it left diagonal, and this one, that I call it right diagonal. Now, if you say the left diagonal, and you intersect with the Dyck path, what you find here is the projective cover of M. If you take the right diagonal, you take the dual definition, which is the injective envelope of M. Okay, why this is important? Because we know that if we want to find the projective modules, we need to find the ones that they coincide with their projective cover. So it's this one, this one, this one, this one, not this one, but this one, this one, this one, and so on. Is this clear? I mean, you take all the left diagonals, you intersect with the graph, and these points are exactly the projective modules. And if you do the same with the right diagonal, you find the injective modules. Also,
Eirini,
you can, yes?
But this is not this is how this is related with the AR quiver of the algebra. Because from the left-hand side, you also have the projectives, right, somehow?
Yes.
So these algebras are of finite type.
Yes.
So you have the projectives, and on the other
and then you have the injectives. And the peaks here are the projective injectives in the composable.
Do you see also the AR translation here, somehow?
No, I mean, the translation is you go from the quiver to the algebra, and then you use the bijection I told you to see them in the Dyck path.
Okay.
Sorry, is it difficult to prove this claim that of finding projective and injective cover, projective cover and injective hull?
What do you mean difficult? I mean, I mean, actually, it's not obvious for sure, and we have used some results of Auslander-Reiter theory.
Okay.
So, I mean, yeah, it's not something that you say, yeah, these are the projectives. No.
Okay. Yeah. Thank you.
Eirini, sorry, there's a question also in the chat. Can you recall what do the colored circles mean? This equation.
What the color? Nothing. I just use. I mean,
maybe you can recall.
Oh, could you repeat the question? Sorry, if it means.
What do the colored circles mean?
Okay, the red one, it's the module I'm going to study in this talk, in this slide. The blue is the projective cover of the red. The green is the injective envelope of the red. And now I'm going to explain the other two. So I stabilize one, I choose one of them, and then I explain to you how I find the projective cover and the injective envelope. Okay, there are two more things that we can see for our modules. We can see the radical, which is the intersection of maximal submodules of M. So how we find this, which is the yellow, I take my module, I find its projective cover, and I go one level above. Now, the CZG I explained to you before, it's the purple. So why this is here? This is more complicated. The level of my module is 2. You see here is 1, here is 2. The level of the projective cover is 4. So 4 minus 2 is 2. So I go to the diagonal of the projective cover and I go to level 2. O propapus to propapu to papu. Anyway, but is this clear? So even if you don't remember exactly how this happens is that if you have an indecomposable module, this is a black dot in the diagram, and then you can find the injective cover, the injective envelope, the projective cover, the radical, the CGG. You have all the information in the graph. So you can read the graph and say things about these modules. For example, here the injective projectives are 4. 1, 2, 3, 4.
There is a question in the chat about why is the CGG indecomposable?
Because this is what I said before. It's isomorphic to an indecomposable module. Because the way I have defined this one is free. So you can find this phi going from a projective to M. And then like that, you can see that this kernel is isomorphic to an indecomposable module of the algebra.
But if we take some redundant generators, like if you take M1 and M2 to be 0, then the kernel will catch a summand of A and I direct sum A n. So if I take M1 to be 0,
you take here.
If I take M1 to be 0,
yes,
then the kernel will have A and I as a summand, as a direct summand. So are we taking some minimal generating set to ensure that the CGG is indecomposable?
Yeah, you mean here instead of a system? Okay, I see what you mean. I see you here to have a minimal system of generators.
Okay, then I think yes.
I think you are right about that. Maybe yes. Because if it's not a minimal, you always take the 0, then this is not what you want. Okay, I see. Thank you for that.
Yes.
So in this definition, is the blue like the red dot is M, the blue dot is ANI to the S, and the CCG, the purple dot, is the kernel? And can you generally build short exact sequences with this in this depiction?
It's not that easy to do that. I mean, let me think. Actually, I haven't done this. How you can... The purple is the kernel. Yeah, I mean, all the things here
you have the module, the cover, and the kernel, the omega of that. So you have it.
You have this one.
Yes.
Yeah, but it seems to... This statement for me seems to imply that if you have like here the module and the cover, you can combinatorially find where the kernel module is. And that seems very interesting. Like,
I mean, yeah, this I haven't done. I mean, I haven't done this. Okay, I will try to think. Okay, yes, you can have the obvious one, the sequence, but which one you mean we built? I think I didn't understand what you asked.
I think Costa says that the omega of your module will always be inside this graph.
Yes, it will be. By the way, it's, yeah. Okay, yeah, this is true. Yes. Okay, now I understand in the sequence. Okay.
So in reality check, all indecomposable modules are these dots, right?
Yes, yes, yes.
We
And
have-
they come from the Kubi series. I think this is so you can see them actually, and then you can play a little bit around of what you have, and you have a lot of information when you have a graph like that about the modules. Okay. So now I'm going to talk to you about the first question we had with René. We take a Nakayama algebra, and we want to study the projective indecomposables, the left diagonal, if you remember, which admit an injective resolution of length k, which means we have exact sequences of this form here. Each xi is injective and this k is minimal. Actually, the question is, if you fix the k, how many p's you can have, admitting an injective resolution of length k. And maybe now you have a question. Okay, very interesting what you want to answer, but why do you have this question? And actually, the motivation here comes from this one. If you take a lattice and you take now a commutative ring with one, you can build an algebra, the incidence algebra. So you take elements of the lattice, x, y, such that if of xy is 0, if you cannot compare x with y. And for this algebra, René and Yama proved that the number of these modules P, I mean, this time I talk about P over this new algebra, not over the Nakayama algebra, which admit an injective resolution of like 1, this small k here is 1, then this is the number of reducible elements of L. What does it mean? It means that you have this complicated number of modules that you want to study, and then you associate that with a simple structure, which are the reducible elements of length. You have a statistic, as we say. So our question was, okay, maybe we can replace the incidence algebra with another finite dimensional algebra. For example, the Nakayama algebra. And okay, we have here a lemma that we reformed our question. It says the following, okay, instead of finding these modules P, which admit an injective resolution of length 1, it's okay, it's the same, to find syzygies, actually projective syzygies, of another module Q, where Q is injective, but not projective. And maybe now it's too much information, but I will show you with a drawing how this can simplify the sec of P. Okay, so I have here white dots because I will put some color. And I have here the levels because we remember for the syzygy, I need to do some calculations with the levels. Okay, here are all my modules. And firstly, I will find the Q. Then I will find the syzygy of Q. And then I will see which of them are projective. And I have the P. Okay, so Q is injective. So I go to these right diagonals. Okay, these are the red. But it's not projective, so I don't allow the peaks. Is it clear why I have the red? So injective, but not projective. Now let's find the syzygies. I will start with the last mountain. So the level of the peak is 6, minus the level of the red is 1, so I am here. The second one, the third, the fourth, the fifth. Is it clear how I found the syzygies? I do the same here. So the syzygies of these 4 are here. The syzygies of these 2 are here. And for this one, it's here. Okay, now I have the syzygies. But I say here in the lemma with René that I need that the syzygies are projectives. Projective means they are here, but not here, not here, not here. So I take this one, because this one is in this left diagonal, the top of this left diagonal, but this is not, because the top is here. Here I have nothing, nothing, and here I have only 1. Okay, so what does it mean? That the number of p here is only 2. So by doing this translation with this lemma, we managed to count all these points, and actually, so here what I did, I rewrote this lemma, but instead of talking about an Nakayama algebra, I put n plus 1 in order to have n Dyck path, because it's easier for me to write the formula. Okay, I give you here the point Q, and here the point P, we have seen the example. What I want to tell you here with this picture is that not all these points P here do the job. I mean, as you have seen here, I exclude some of them. But okay, these are the possible positions. So then our theorem is the following, that this number of P is n if your Dyck path is just a mountain, up and down. And it's this complicated formula if it's not. So I will explain a little bit the formula. I use only n1, which is the first up, the first down. Okay, and here I have ni. Ki is the level of this dot here, and ml is the number of the last ups. Okay, so we have a formula, but I promise to you that we want a simple structure, we want a statistic, and this is not simple. I mean, okay, of course it counts these points, but it's not as nice as before that you had the reducible elements of the lattice. And in order to do that, in order to have something better here and to explain a little more, we used another combinatorial object. And before I do that, I will tell you the second question and we see both of them. So in the second question, I'm going to study J is the radical Jacobson we have seen before. I'm going to study this space of extensions, which it means that I'm going to classify these exact sequences here. And this is a classical problem in homological algebra. Makis knows more. So it's very common to study this space, especially for the Jacobson radical. So the reason we wanted to study this is because we have found that the dimension of the space when small k is 1 again is not 0. So our question was, okay, if it's not 0, what it is? What is this dimension? Okay, so we did again a translation. This time I don't want to explain to you again. Instead of finding this dimension, this is the end, the number of vertices minus a number here, which again are some modules and some CGGs and a story like that. And we had again a formula that, okay, looks like the one we had before. But as I told you, these two formulas don't give us the elementary structure we are looking for. So we want to seek that by using another combinatorial object, the so-called pattern-avoiding permutations. Okay, so in order to do that, I'm going to explain to you what is pattern avoiding. I will start with a sequence of distinct positive integers, as I have here in the example. And now what I do, I want to write this number in increasing order. And instead of talking about 8, for example, I'm going to talk about the number it has in this increasing order. So the smallest one is 1. Then it's 3. So for 3, I write 2 because it's the second. Then the 5 is the third. 7 is fourth. And 8 is the fifth one. So if I take now this one and I put it here, I construct a permutation. So I start with a sequence of distinct positive integers, which is not a permutation, and I construct a permutation. Okay, which is called the reduction of W. So people who do combinatorics know that, but sometimes instead of writing a permutation like that, I just write the second line. So now I take a permutation Sn, and I take another one, tau, in Sm, where m is smaller or equal than n. Sigma is my permutation, and tau is my pattern, what we call pattern. We say that sigma avoids tau if there is no subsequence here of m indices such that the reduction of sigma I1, sigma I2, etc. is tau. So in practice, it means that if you are here in this line of the permutation and you choose m elements like that, m arbitrary elements, and you take the reduction of these arbitrary elements, you don't have tau. So when I started working with these pattern avoiding permutations, I couldn't understand the word pattern until I went to combinatorics conference some weeks ago, and someone gave this picture and it made clear to me. So I stole it. No, I asked. I didn't steal it. If you write your permutation like that, I mean, you have here 3, 2, 4, 6, 1, 5. So 1 goes to 3, 2 goes to 2, etc. And here you have your pattern, 2, 3, 1. You don't want to, you say that sigma avoids tau if you cannot see this pattern inside here. So here, as you can see, doesn't avoid because you can find the pattern here. For me, another way to understand this is when I talk here about the pattern 2, 3, 1, it doesn't matter it's 2, 3, and 1. What it matters is that 2 is smaller than 3, which is bigger than 1. So I have something like medium, large, small. So if I have this permutation, whenever I choose 3 numbers, I never have medium, large, small. Or I have medium, large, small. This means contains or avoids. Okay, in this talk, we're going to use the 3-to-1 avoiding permutation. So every time I have a permutation, I don't want to have large, medium, small. And if you enumerate all the 3-to-1 avoiding permutations, you have again the Catalan number. So there is a theorem here that says that there is a bijection between the Dyck paths and the 3-to-1 avoiding permutations. And again, since you have the same number of elements, of course you have a bijection. But actually, Billy, Jocus, and Stanley constructed one. I want to tell you here that we have more bijections between these objects. And keep that because I'm going to use it later. Okay, so how they constructed this bijection? What they did is that they took the Dyck path. You write here the number of ups. Then you take 3, then you add 3, you have 6. You add 1, you have 7. So here it tells you that up till the second mountain, you had 6 ups. I don't write the last one because every time you add the last one to the whole sum, you have n. And then they added 1. They did the same with the downs, but this time they didn't add 1. And then in order to construct the permutation, which avoids the pattern 3-to-1, in the blue positions, they come from the down. They put the red ones, they come from the ups plus 1. And the rest, increasing order. Okay. So let's see again the first question we had about these modules. With René, we have proven that when k is equal 1, this small k, then this number with this complicated formula I talked to you before, it's exactly the number of fixed points of P. So yes, we have our statistic. And we have something even more here. Because, you know, for the 3-to-1 avoiding permutations, we don't know the number of fixed points. Actually, it was an article talking about the distribution and the probability to have this number of fixed points, but we don't know them. Now we use the formula from before and this theorem to give a formula for the fixed points. So I give you here the definition of an exceedance of P are all the integers j, such that P of j is bigger than j. So if you have I1, Ik, the set of exceedances of P, if P is the identity, you have n fixed points, okay, we knew that. And here I have a formula using only these exceedances to find the fixed points of the permutation P, which avoids the pattern 3-to-1. Okay. And when k is equal to 2, we knew nothing, but we had a conjecture from 2 weeks ago. So if you have a Dyck path, you can define here some pyramids. We call them maximal pyramids. And the pyramid weight is that if you add the lengths of all these pyramids, so with René, we conjecture that for k is equal to 2, the number of these modules P we were looking for is exactly this pyramid weight plus 1. And we have proven that until n equal to 10, but yeah, not anymore. Okay, so if we go now to question 2, that we study this space of exceedances, if the small k is equal to 1, we have n, the number of vertices of the algebra, minus the cardinality of a set that comes from combinatorics, and it's called the support of a permutation. And we can do even more here. So if we take our permutation and then we write it as a product of these transpositions, that I goes to I plus 1, then we say, okay, and this product is minimal, then we denote with S the distinct generators that appear. For example, if you have S4, S3, S2, S5, S4, then this small s is 4 because we use only 5 generators, which are different from each other. And then with René, we have proven the dimension of the space when k is equal to 1 is actually this small s. And for k equal to 3, we have nothing so far. So we have checked and we don't even have a conjecture here. Okay, so I think this is all I wanted to say. And thank you very much.
Thank you very much, Eirini,
Thank you, Eirini.
for your very nice talk.